AI philosophy, enabling humans to establish destiny for themselves and establish a mind for AI. The Connectionist school, also known as the neural network school, has its core idea rooted in simulating the distributed parallel computing and self-organizing mechanisms of the neural network in the human brain. Unlike the Symbolist school, Connectionism does not rely on manually predefined, explicit logical rules. Instead, it automatically learns deep-level features and patterns through a data-driven approach. The advantage of the Connectionist school lies in its powerful learning and generalization capabilities. Its disadvantages include poor interpretability, the black box problem, a heavy reliance on large amounts of data, and unstable training processes. Click the plus sign to follow this account for more exciting content. Connectionism, also known as the neural network school, has its core idea rooted in simulating the distributed parallel computing and self-organizing mechanisms of the biological neural network in the human brain, as shown in the figure below, and in section 5.27, Deep Learning. Thinking deeply like the human brain. The human brain does not have a single central processing unit. Instead, it processes information through parallel connections between individual, slowly running neurons. Furthermore, the brain often experiences a loss of connections between neurons, but this usually does not negatively impact brain function, suggesting that many details are not critically important. Connectionism posits that the essence of intelligence lies in the complex connections and interactions between a large number of simple units, neurons. By adjusting the weights of these connections, the system can learn patterns and regularities from data, thereby achieving intelligent behavior. Unlike the Symbolist school, Connectionism does not rely on manually predefined, explicit logical rules, but automatically learns features and patterns through a data-driven approach. Representative technologies of the Connectionist school include multi-layer perceptrons, MLPs, deep learning, convolutional neural networks, CNNs, recurrent neural networks, RNNs, and generative adversarial networks, GANs. Deep neural networks, DNNs, are quintessential example of the Connectionist school, utilizing multi-layered neural networks to automatically extract features from data, achieving tremendous success in fields such as image recognition and natural language processing. The foundational algorithm of Connectionism is backpropagation, which updates the weights of the neural network by calculating the gradient of the loss function. The developmental history of neural network architectures has involved progressively increasing depth, from the earliest single-layer neural networks to two-layer networks, and then to breakthrough multi-layer networks, i.e. deep neural networks, which is when they truly began to become practical and powerful, as illustrated in the figure below. The advantage of the Connectionist school lies in its powerful learning and generalization capabilities, using large-scale parallel computing to process high-dimensional, nonlinear complex data, and being able to learn deep patterns from vast amounts of information. Early on, it was limited by computational power and data scale. Later, breakthroughs in the transformer architecture, such as the GPT series, enabled it to dominate generative tasks. However, it also faces challenges such as poor model interpretability, a heavy reliance on large amounts of data, and unstable training processes. The decision-making process of neural networks is often viewed as a black box, making it difficult to understand their internal workings. The complex structure and weight adjustment mechanisms within neural networks are often hard to explain, making model understanding and debugging difficult, which can lead to trust issues in critical fields like healthcare and finance. Furthermore, deep learning training typically requires vast computational resources and labeled data, limiting its application in data-scarce scenarios. To overcome these limitations, researchers have proposed techniques like explainable AI, XAI, and few-shot learning, continuously explore new network architectures, optimization algorithms, and regularization techniques, while also incorporating ideas from symbolism to develop methods such as explainable neural networks and knowledge distillation, aiming to enhance model transparency and reliability while maintaining performance. I am Wu Huayu, a PhD from the Chinese Academy of Sciences and a postdoctoral fellow from Peking University, and the founder of AI Philosophy. For more detailed information, please refer to the complete version of this book. In addition to this short video, you can also click on my avatar to view more long videos.